Hello. Now we'll study the conduction in detail. So as we have studied in the previous topic, previously, that during the conduction, the sender and receiver exchange the heat with the help of medium's particle. And the medium's particle, they only vibrate with respect to their mean location. They don't move along with heat. Only the heat moves. So in case of conduction, we divide that conduction into two subtopics, before steady state and the after steady state. The explanation before steady state is different and the explanation after steady state is different. So this is before steady state. So before steady state, there are these medium's particle. I have represented them by 1, 2, 3, 4. And these 4 particles will be having the same temperature, because if they will not be having the same temperature, heat between themselves will start to transfer. So if they are having the same temperature, there will be no heat exchange happening between them. So the sender and the receiver, this is the inlet for us. Inlet in the sense the heat will be coming from here, and this is the outlet for us, meaning heat will be taken out from here. So sender, when it comes into contact with particle 1, it gives the heat to the particle 1. I'm saying that heat as Q. So the Q heat was provided by the sender, and it's a continuous amount of heat the sender will provide. The Q heat was provided by the sender. So before that Q heat, this particle 1 was vibrating. It was having its own temperature. It was vibrating. So let's draw their zone of motion. So this is the zone of motion. This is the zone of influence for 2. This is the zone for 3. And this is the zone for 4. Now, zone means the particle were vibrating in this zone, and the particle 2 was vibrating in this zone. And there was no overlapping because they were steady state. In between, they were at steady state. So the moment sender provided heat to the Q will receive that heat. It will consume that heat for a time being, obviously, and its vibration will increase. When its vibration will increase, its zone of influence is going to increase. So which was this, in this case, the zone of influence will increase. When the zone of influence will increase, it will start affecting the particle 2. So this particle 1 vibrates more. Then it starts affecting particle 2. When it starts affecting particle 2, some of the heat or energy will transfer to the 2. I'm calling this 1, Q1. So because it is affecting, it's like crowded place and one guy is moving. So because of that one guy, all the other guy will also start moving. They have to move. So the particle 2, when it gets affected by 1, it receives some energy, Q1, from the 1. And the moment the particle 2 will receive this energy, its own zone of influence will also increase. Not like 1, little less than 1, because it is not getting the same amount of heat the 1 was getting. So because the 2 will have the bigger zone of influence, the 3 will also get affected. And when the 3 will get affected, this is when the 2 will give the Q2 heat. So the thing is, getting affected is, in a way, is transferring the heat. So the motion of 2 is affecting the motion of 3, and that's how the heat gets transferred. That's how the energy gets transferred in terms of kinetic energy. And the same will happen for 4 also. And the 4, let's say, is giving Q dash heat to the receiver. Now, if you can see here, the particle 1 is getting the Q heat. It is sending the Q1 heat. So this Q minus Q1 heat, where this heat is going. And similarly for 2, Q1 it is getting and the Q2 it is sending. So Q1 minus Q2 for the second, where that amount of heat is going. So the Q minus Q1 amount of heat is being absorbed by 1. It is being absorbed by particle 1. And because of this absorption of this heat, the temperature of the point 1, particle 1 will increase. So it will be having more vibration. Okay. So this process, if you have seen, the Q was the amount of heat sender was sending, and the Q dash was the amount of heat receiver was receiving. So Q minus Q dash was being absorbed by the medium. So this Q, the sender is sending the heat continuously. So one more time it will send the heat. One more time I'll draw these particles. 1, 2, 3, 4. So once again the particle 1 receive Q heat. So its zone of influence, which was till this point, it will further increase. And when its zone of influence further increase, it will further influence the particle 2. So during that influence, as we already know, it will transfer the heat, and I'm calling that Q1 dash. I'm not saying it will be equal amount of heat, it will transfer, because both the cases are different. They were having different temperatures there. Similarly, zone of influence of 2 will increase, so 3 will get affected, and the Q2 dash, similarly Q3 dash, and will have Q double dash. So one more time, when the heat was provided to the sender to the medium, heat is getting transferred from 1 to 2 to 3 to 4 by the increasing of zone of their own influences. So in terms of kinetic energy, some portion of heat transferred to 2 in terms of kinetic energy, then 2 to 3 in terms of kinetic energy, and finally received by the receiver. One point we have to see here, this time the particle 1 is absorbing Q minus Q dash heat. The thing is, this is the heat particle 1 is absorbing, Q minus Q dash. So it is sending the Q1 dash. So this Q1 dash, the amount of heat transferred by the 1 this time, the Q1 dash will be more than Q1. The second time, particle 1 will send the more amount of heat to the particle 2. Similarly, particle 2 will also send more amount of heat to the particle 3, that is Q2 dash. So the Q2 dash will also be more than Q2. So amount of heat absorbed by the particle 1 or 2, and second time, which is Q minus Q1 dash, it will be less than Q minus Q1. And same will be for the particle 2. This time particle 2 will absorb less amount of heat. So each and every particle will absorb the less amount of heat second time. So the amount of heat absorbed by the whole medium, which was, if you remember, Q minus Q dash, that was the amount of heat. Q was given by the inlet and the Q dash was taken out by the outlet. So the Q minus Q dash was the amount of heat absorbed by the whole medium. So this time the Q minus Q dash, the amount of heat absorbed by the medium in beginning, that will be more than the amount of heat absorbed by the medium next time. Or I can say the next time, second time, the medium will absorb less, transfer more. And same will be happening for the third time. So with time, the amount of heat absorbed by the medium will be less and less. So finally there will be a time when the amount of heat given by the sender and the amount of heat received by the receiver will be same. So after achieving the steady state, the amount of heat given by the sender, I am calling that QS, will be same as the amount of heat received by the receiver. I am calling this QR. They will become same. The same amount of heat, whatever amount of heat the sender is giving, the same amount of heat will be taken out by the receiver after achieving the steady state. So let's make the picture. So after steady state, let's see what will happen. So there will be particle 1, particle 2, particle 3 and particle 4, and there will be our receiver and there is our sender. So the particle 1 will be having temperature T1, T2, T3 and T4. They are the temperatures of these 4 medium particle. So after achieving the steady state, the system will be providing, or sender will be providing Q amount of heat to the T1. But with that Q amount of heat, the particle 1 will be having its maximum vibrational zone corresponding to the Q amount of heat. If you increase the further Q amount of heat, all things will get rearranged. So it will not take any heat out of this given heat. So it will transfer complete amount of heat. Same will do the 2, 3 and 4. So each and every particle will be at their maximum zone of influence at that time, maximum zone of influence corresponding to this Q. If you increase the amount of heat given to the system one more time, the steady state will be disturbed, and one more time this whole process will go on. So after achieving the steady state, each and every particle will be at their maximum zone of influence, so they will not absorb any more heat. So whatever heat they are getting, they will transfer the whole amount of heat to the next particle, and through this process the heat will reach to the receiver finally. Okay, so this is the case, and at this state, if you see, at this state the temperature of 1 will be more than temperature of 2, will be more than temperature of 3 and so on. The particle which is in contact with the source or sender will be having the maximum temperature, and the particle which will be in contact with the outlet or the farthest away from the sender will be having the least temperature there. Okay, So this is the case. After steady state, that's what happened. Now we want to make the formula. To make the formula, we will convert this medium into a simpler medium. So for us, I'm taking a linear object. Linear object is there. It can be a rod kind of object, and here you are having the sender or inlet, and here you are having the receiver or outlet, and this is my medium. The length of the medium is L, and the cross section area I'm defining as capital A. So sender, after achieving the steady state, obviously after achieving the steady state, sender will be sending the Q amount of heat. I'm using the dot here. This dot represents dQ by dt. This is the rate of heat flow because this heat is given continuously. This is dQ by dt. And at the same time, receiver will receive the heat, and that will be same because after steady state, both become same. Okay, so the amount of heat given by the sender, rate of amount of heat given by the sender and the rate of amount of heat received by the receiver will be same after achieving this steady state. So at that state, every point, this point will be having higher temperature, this point will be having lower temperature because we already studied that. So this heat we want to calculate. So what we will do, we'll go for x. From the sender, we'll go for x, location x, and we'll cut an element of dx length. Okay. So temperature here, since it is decreasing, temperature here I'm assuming as Tx as a function of x. So temperature here will be equals to Tx minus of dt. Because see, as you are moving away from the sender to receiver, the temperature is continuously decreasing. So dt is the drop in temperature corresponding to this width, dx width. Okay. So after achieving the steady state, and when we have uniform cross-section medium, if I calculate the Q, this Q is proportional to A. First of all, it's a cross-section area. Now, why it is proportional to A? As you can see here, this sender is giving heat directly to the one particle. More number of particle, more amount of heat the sender will be able to give. And the number of particles here at this here will be proportional to the cross-section area. More will be the cross-section area, more number of particle will be here. So that's why this Q, amount of heat given by the sender to the receiver, is proportional to the cross-section area. It is proportional to the temperature gradient also. Gradient, not rate. Temperature gradient means how fast the temperature is decreasing as you move towards the receiver. You see, if there will be higher temperature gradient, the amount of heat will be more there. The more amount of heat, the faster rate of heat will be getting transferred from the sender to the receiver. Okay. So if you combine these two, on combining, we'll have Q proportional to A dt over dx. Upon combining, we'll have this relationship. So we have to introduce a proportionality constant here, and obviously we have already accounted for the dimensional aspect, that is A and dx. That is the dimension of medium. So we need a constant which will account for the internal property of the medium. So that is K, that we define as K. So Q is equals to Ka dt over dx. That becomes the formula where this K is completely independent of external properties or dimensional properties of the medium. It only depends upon internal properties of medium. Internal properties means the density, what kind of material it is. Medium, internal property of the medium. This K is known as conductivity constant or coefficient of conductivity. Conduction constant or coefficient of conductivity. Its value is generally provided to you by the examiner. He will always provide you this value. The cross-section area also he will provide you, and the dt over dx he will also provide you. Sometimes he provide the temperature as a function of x. So in that case, by differentiating that function, you can calculate the dt by dx. And if you put the value, you will be able to calculate the amount of heat which is getting transferred at that instant. And as you can see, if the dt over dx is 0, and that will be 0 if the medium throughout is having the same temperature. If dt over dx is 0, the amount of heat Q transferred will be 0. So you see, to transfer the heat through the medium, with the help of conduction, through the process of conduction, you need to have a temperature gradient. If you don't have the temperature gradient, the heat will not get transferred. So, you see, one more time we want to summarize this thing. We were having the sender and the receiver, and the particles were there. And this was before the steady state. So, since sender was in contact with particle 1, it provided the Q heat. With the help of, with the taking of, when the one particle takes the Q heat inside, it vibrates more, because the vibration or kinetic energy of the particles is proportional to the energy they receive. So when they will vibrate more, it will start influencing the particle 2. It is similar to the concept as a classroom concept. They are like a class. They are within the class. And the class is completely packed. So if any one of the students start getting excited, it starts moving. So when he starts moving, it starts affecting the others. So the thing is, the moment the one particle will be moving, other particle tends to move. There is some portion of the kinetic energy of the particle 1 will transfer to the 2 because of their collision, you can say, or the influence. So the particle 2, through this process, the one particle will provide the Q1 heat to the 2, and same thing the 2 will do to 3, and it will go on. So the Q minus Q1 is the amount of heat absorbed by 1, and similarly Q1 minus Q2 will be the amount of heat absorbed by 2, and it will go on. So the sender is not giving the heat in one go. One more time it will go, it will give the heat to the 1, and similarly the next time when the Q heat will be given to the 1, it will transfer the Q1 dash heat, and this Q1 dash will be little bit more, it will be little bit more than the previous case, because this time the one particle little bit more satisfied. And the same thing will happen with 2 to 3 and 3 to 4, and it will go on. So there are two things, the amount of heat transferred by the 2 to 3 and the amount of heat retained by the particle. So with time, the particles will tend to transfer more and more heat, and they'll tend to receive or retain less and less heat. So the energy received or heat received by the medium with time is going to decrease, and finally there will be a time when medium will not retain any amount of energy. It will send whatever amount of energy it is getting. Okay, so that's this case. Then we did the formulation. We took this case where we had the linear medium we had, and the Q heat was transferred through it, and the Q heat was received through it. And the formula we made, this was the formula, and the K we defined as internal property of the medium, conduction constant. Thank you.